Namaskar and welcome back to another lecture in this course on infrastructure asset management, which I am offering with my colleague Professor Chirag Kothari under the MOOCs initiative of the Government of India. This week we are talking about asset management, inspection, evaluation and action. The lecture today is titled Non-Destructive Testing and Evaluation Methods for Concrete Structures. A warning as usual, the material being used here is strictly for academic purposes and should not be used for any other purpose. What you see on the screen is like the blackboard of the good old days, and please make it a habit to make notes and use what is being visually projected and what is being orally stated together. Now, as far as this course is concerned, we have talked about an overview of the course, we have talked about a schematic representation of deterioration and performance versus time graphs, and the examination of the concept of service life and maintenance action in that framework. Through hypothetical case studies, we have highlighted the role of different stakeholders in different phases of the project and the importance of a comprehensive strategy towards the management of infrastructure assets. We have also talked about decision making frameworks, including performance modeling considerations in budget allocation. In the last module, we discussed some deterioration mechanisms, basically carbonation and chloride induced corrosion of reinforcement, that is primarily in the case of concrete structures, and the measures taken to ensure their durability. Now, moving forward, as far as our discussion today is concerned, in this module we are focusing on inspection, evaluation and action, with the focus being concrete structures. The idea is that once we understand concrete structures, then similar concepts can be developed for other structures such as roads, which could be bituminous, or for that matter steel structures. As far as the discussion today is concerned, we saw the overall strategy in this context in the last lecture. Today we will talk about an outline of some of the commonly used methods for non-destructive testing and evaluation used in concrete structures. Now, as far as the non-destructive testing methods for concrete structures are concerned, we should remember that concrete structures are large structures, and the testing methods can in principle be classified as general purpose methods and special methods as far as testing is concerned. As far as the former, that is the general purpose methods are concerned, they can be used to get a general understanding of the overall health of the structure. They could be used to identify a mechanism of deterioration involved and narrow down areas for more detailed inspection. The latter, which are special methods, can be then used to get more specific information about the extent of deterioration on account of a specific mechanism of deterioration in a local area. Engineering judgment is then needed to integrate the information obtained and make an overall evaluation and finally decide the course of action. And therefore, as far as the objectives of non-destructive testing are concerned, we could be talking about the strength of concrete, we could be talking about cracking in that concrete, we could be talking about delamination or voids behind a concrete surface. What we are talking about here is a situation that if you have a tunnel lining something like this. So, this is where the tunnel is, and there could be vehicles or whatever it is moving in this tunnel. Now, this thickness is the concrete. Oftentimes behind this surface, that is somewhere here or somewhere else, there could be pockets or voids, and they need to be identified. That is what is meant by voids behind a concrete surface. So, the surface looks all right, but what we have to see is whether this thickness of concrete is what is required, whether in this thickness there is a void and so on and so forth. We could be interested in the thickness of the concrete layer, that is what I just mentioned, that what exactly is the thickness here. It need not be uniform all over the place. So, these are the kind of things which we require to do when we are trying to do a non-destructive evaluation of concrete thickness or the integrity of concrete in a tunnel lining. So, this is a very specific example of how non-destructive testing, for example, will work in the case of tunnel structures. We could be interested in the permeability of concrete in situ. We could be then interested in the corrosion of reinforcement. What is the extent of corrosion? What is the rate of corrosion? So, these two things are very different. Whether a bar or a reinforcement has corroded or not is one question. Even if it has corroded, is it still corroding? And if it is still corroding, what is the rate at which it is corroding? So, these are some of the questions that require an answer. Not that they can all be answered unambiguously, reliably through non-destructive testing, but yes, the efforts need to be directed in that direction. We could be interested in determining the depth of carbonation or the chloride penetration in concrete, or we could be interested in the alkali aggregate reaction in the concrete. Moving forward again, as far as traditional methods of non-destructive testing are concerned, and that is what we are going to be primarily talking about today, as far as the estimation of strength is concerned, primarily we deal with these two methods, Schmidt hammer and ultrasonic pulse velocity. In certain cases, we try to use the pull out and pull off tests. Then at times we use a reinforcement locator. We should remember that as far as reinforced concrete structures are concerned, we know that if this is the environment that we are talking about, then the reinforcing bar is located at a certain distance from the surface. Also, if you look at this kind of a wall from the front, you will find several such reinforcing bars. So, what we need to do is to find the exact location of these bars, and that we have to do from the surface. So, this is what is the function of a reinforcement locator, and it uses electromagnetic methods to be able to do that. So, once we have this map, we can use it for other tests, as we will talk about later. As far as the corrosion is concerned, the most commonly used method is that of natural half cell potentials. Then we could be carrying out in situ examinations of such a concrete structure using surface drags and delamination and chain drags and so on, and we could be using methods to determine the in situ permeability of concrete. Now, these permeability methods are not very commonly used, at least now, and I am not going to cover them in the discussion today. Moving forward, as far as the more recent developments in non-destructive testing is concerned, we can use infrared thermography, we can use image processing, acoustic emission, impact echo, in situ permeability of concrete I just talked about in the previous slide. We are using dynamics based structural health monitoring tools, which could be active or passive methods. Now, of these, only these two is something which we will touch upon today, and these I am having to leave to you as an assignment. The idea is only to discuss some of the commonly used methods and highlight their technical limitations, applicability and so on. At the end of it, this course is on infrastructure management, and the larger picture is that yes, we need to do non-destructive testing. What specific method to use, what is the kind of information that we get from it, that is something which is sometimes very technical and had better be left to technical people, and therefore, a more detailed discussion on some of these methods will probably need a separate discussion, which is not really a part of this course. Nowadays, we often talk about application of drones in the collection of data. We talk about using embedded sensors for real time collection of data. Now, as far as this is concerned, there is always the challenge of life, that is, how long will these sensors continue to send reliable data? What will be the method of sending that data? What will be the method of collecting that information, and so on and so forth. So, these are some of the challenges, and some applications you will always find in certain specific structures. In this course, we are talking about a more generic system which is more applicable to all structures, and therefore, by design a detailed discussion on some of these aspects has been left out as far as this course and this lecture is concerned. Coming to the first method, which is the Schmidt rebound hammer. This picture here shows a rebound hammer being used on a cube of concrete. Now, possibly in another lecture in this course, we will have a demonstration where we will show you how the hammer works, but the principle is that this hammer is used to rebound a probe onto the surface of concrete and we get a reading. The method is based on rebound from a hard surface, and the assumption is that a concrete with a higher strength will have higher surface hardness and therefore yield a higher rebound number. So, what we want to do is to get an idea of the strength of this concrete. We use a rebound hammer to get the extent of the rebound, and that extent of rebound is related to the surface hardness here, and the assumption is that this surface hardness here is indirectly related to the strength of concrete. This picture here shows a calibration of the actual compressive strength and the rebound number. So, you will notice that this 30, for example, does not correspond to this 30 here, or this 40 here does not correspond to the 40 here. So, for each hammer we need to have a specific calibration curve, and not only that, this calibration curve has to be periodically updated. There is also an element of the person who is carrying out that measurement. So, these are some of the things that we need to keep in mind. The rebound hammer test is a very simple test. It can be carried out the way it is shown here, that is the hammer pointing downwards. Here the hammer is horizontal. Also, it can be used when it is pointing upwards. So, in this application we are trying to get the strength in a slab from the top. Here we are trying to work with a wall, and here we are trying to get the strength of the slab from the bottom. So, it can be used in different positions, it could be inclined as well, but as I mentioned, in the absence of theoretical relationship with the compressive strength of concrete and rebound, calibration is very, very important. Also, over a period of time, the spring which is built into this hammer undergoes changes, its stiffness changes, and the moment that stiffness changes, this calibration curve also changes, or it could change, and therefore, it is important that not only we use the calibration curve, but we calibrate it periodically. How that calibration is carried out is something which is given in the standards, and I am leaving it to you to look it up. So, of course, there are a lot of advantages in the Schmidt hammer test. It is easy to carry out, cheap, robust, not very skilled personnel are required, and it is a good tool for comparing two surfaces. The disadvantages are that it is not directly related to strength and is affected by cracking and moisture content of the concrete, near surface aggregates and so on. At best, it measures the strength in a local area. Interpretation of data, especially in terms of strength, is difficult, as variations could be large and the rebound number obtained needs to be corrected for several factors. So, what is stated here in the disadvantages part is that if we have a concrete surface here, there is always a possibility that the aggregates will be at times very close to the surface, because this is the concrete surface and here is where we are going to do the rebound at different points. So, it is likely that if the aggregate is very close to the surface versus a situation where the aggregate is inside and here we have only mortar, the rebound numbers that we get are different, and that is something which needs to be accounted for statistically. Similarly, if this concrete was wet, that is the pores in this concrete were saturated, that will impact the rebound. Also, if this surface had some cracks. Now, as far as cracks are concerned, if there is a concrete surface and we have cracks at different places, these cracks could be surface cracks or they could be deep cracks, in which case the concrete in this part which is bounded by cracks or in the neighborhood of these cracks, these places will yield a different hardness. And unless our procedures to estimate the strength, see, because ultimately what we are going to do is to get some rebound numbers and try to estimate the strength. Now, unless this procedure to estimate the strength from these rebound numbers takes into account the variation that may arise on account of some of these things, this estimate is always going to be in error. So, that is why I said that even though there are a lot of advantages as far as this method is concerned, it is not so easy to just get the strength of concrete in any structure. Apart from that, this method requires access to the concrete surface. Now, this access means that we have to physically create an arrangement through which the concrete surface will be reached, so that this rebound test can be carried out. That is not sometimes very easy. It becomes, or it could become, an expensive proposition. Also, in the case of concrete structures, which are large structures, which have a large surface area, there is always a limit on which this test can be carried out, and that is something which we will probably talk about in a separate discussion. Moving forward, let us look at the ultrasonic pulse velocity. Now, this also is a very commonly used tool as far as non-destructive testing and evaluation of concrete structures is concerned. This method provides an understanding of the medium, that is, the state of this medium. The method basically involves two sensors. Through one sensor, we transmit a wave that travels through this medium and is received by this sensor. So, the method basically gives us information about the state of the medium, which in this case is concrete, and the compressive strength is related to pulse velocity which is recorded. So, typically the way it is shown, this is the distance, and we can record the time it takes for the wave to travel from this point to this point, and we get an estimate of the wave velocity, and this wave velocity is somehow related to the strength. Now, how this happens is something which I am leaving out for you to think or find out from specialist literature. As far as engineering is concerned, this can be taken as a black box, that yes, we get the pulse velocity and we can estimate the strength. The way it is shown here, it is a direct measurement, but remember that this may not always be possible. For example, if we have a slab, then it may not be possible to access both the top and the bottom of the slab. So, in those cases, we have to make do with what is called the indirect measurement. In that method, both the transmitting sensor and the receiving sensor are on the same phase, except that the path length then is more difficult to estimate. It may not correspond to a straight path here. So, these are some of the things for which we need to carry out appropriate corrections, and obviously there will be interference from the presence of reinforcement in the path. For example, in the case shown here, if there was a lot of reinforcement, then it will be very difficult to argue that this wave is passing only through the concrete. If the reinforcement is aligned along the wave propagation, then whether the wave is travelling through the concrete or whether it is travelling through the reinforcement, those are the kind of questions that will be raised and interpretation becomes difficult. So, we have to be very careful as far as drawing firm conclusions only from the ultrasonic pulse velocity recorded. And this has been taken from Indian Standard 13311, and it talks of velocity criteria for concrete quality grading. So, you can see that it refrains from trying to relate it to the strength of concrete. So, they are not talking of the strength, they are talking of some kind of quality grading. In fact, if you read literature, you will find that a lot of people insist that the ultrasonic pulse velocity at the end of the day gives us an idea about the homogeneity and quality of concrete rather than strength per se. So, that is something which you need to be careful about when you are trying to do interpretation. Having said that, There is also a clear mention as far as the Indian standards is concerned that so long as the mixed proportions and the testing conditions are all known to us, we can indeed try to relate the pulse velocities that have been obtained to the compressive strength of the concrete, much in the same manner as the case of the rebound hammer. Moving forward, let us talk about the pull-out method, which is another method for determining in situ strength. Both the Schmidt hammer and the ultrasonic pulse velocity were indirect methods of strength. Now, this pull-out method is a more direct method of measuring strength in situ. What the test does is that there is an embedded rod with the tip here, and we try to pull this rod out. That is the way this test works. And when this is pulled out, there are different mechanisms of failure. It will cause this kind of a frustum of a cone of concrete coming out together. There are other modes in which it could fail, but that is something which I am leaving to you to think about. The method is semi-destructive and obviously can be carried out only in a very limited number of locations. If we have reinforcing bars in this place, this method becomes very difficult to operate. Obviously, it requires pre-embedded probes. That is, we cannot suddenly decide that we will carry out a pull-out test in a concrete structure to determine the in situ strength. Also, the force that we require, which is given as P here, I am trying to write it as F here, this force is related to the strength of concrete here. Yes, this force is related to the strength of concrete, that is true. Now, the mechanism of failure is not something which will give you the compressive strength. Now, that is something which is a separate discussion and we will take it up shortly, but remember that strength of concrete that we normally talk about as far as engineering is concerned is compressive strength. We take a cube and test it in compression, determine its load at failure, and we get this strength. There are different ways of relating it to the so called characteristic strength, that is something which we are not going into, but the discussion here is that this method, this force which causes the concrete to fail is only indirectly related to the compressive strength. Moving on, let us talk about the pull-off test. Now, this pull-off test is a slightly modified version of the pull-out test. In this case, a hole is drilled and tensile fracture is induced as shown. Now, what is done is drill this hole and try to have a probe or a plate adhere to this surface, and we make an effort to pull this plate out. Now, either at the application of that load, the failure will occur here at this surface, which is basically the failure of the epoxy adhesive that we have used, or it will cause a failure of the concrete here, and that is more or less a tensile failure as far as concrete is concerned. This tensile strength of concrete, that is in direct tension, this is not usually measured as far as normal quality control procedures are concerned. When we talk of tensile strength of concrete, we usually talk of the split cylinder strength. Now, that is not direct tension. These are some of the technical details which technical people know, and from the management side it is important to appreciate and have an understanding that when we talk of the tensile strength of concrete, it is a valid question to ask what method. Normally, when we talk of tensile strength, we would expect direct tension, but that is not the understanding as far as concrete engineering is concerned. This too can be done only in limited numbers. The test is semi-destructive in nature. Having said all that, the test is very useful to assess adhesion of tiles fixed to the surface. So, if we have a situation or an application where on this concrete surface we are putting a lot of tiles, and those tiles should be adhering to the concrete surface properly, for that kind of a testing this method is very apt. What we do is fix the tiles, try to pull these tiles off. If the adhesion is good, it will cause some damage to the concrete surface here, but it will show that the adhesive is all right. And that takes us to the discussion of test methods and specifications, that if we have tile fixing as one of the processes involved in the construction of an RC building, then as far as the tile fixing is concerned, the adhesion of those tiles is concerned, we can use this method, but we need a specification. We need an acceptance criteria that okay, the adhesion of the tiles to the surface will be acceptable if this force exceeds a certain number. That is how engineering will work. That is how the initial integrity part of it works. Moving on, we had a brief discussion on different strengths of concrete. We talked about the compressive strength, we talked about tensile strength, we talked about direct tension, we talked about split cylinder, we could talk about flexural strength and so on. Now, very often as far as quality control is concerned, we carry out different tests. It is important to know and understand that at the end of it there is a relationship between these parameters. This graph for example shows experimentally determined tensile strength and compressive strength values. So, if we can see that this number here varies between let us say 15 and 20 against a compressive strength of 200. So, typically the tensile strength is about 10% of the compressive strength that we get from the usual testing. Similarly, this is the relationship between the tensile and flexural strengths of concrete. This is the line of equality, that is 10 corresponding to 10, 20 to 20. What it shows here is the flexural strength that we get is higher than the tensile strength. Now, the flexural strength is determined by a test which in principle looks like this, that we have a beam like specimen subjected to this kind of loading. It could be 3 point as shown here, it could be 4 point, which would mean that there are 2 points where the load is applied, inducing failure here. So, this crack will propagate and there will be failure, and this failure initiates because concrete is weak in tension. So, in a manner of speaking, yes, the flexural strength is related to the tensile strength, but is not the same thing. We can say that we determine the tensile strength using split cylinder or a flexural test, but that sometimes is referred to as the flexural strength. That is a matter of technical detail and has been included for the sake of completeness. Moving on, so far we talked about the strength of concrete. Now, we are going to talk about measuring cracks in concrete. We said that yes, concrete structures often have cracks, sometimes they are expected, sometimes they are not expected. So, in any case, sometimes we need to measure these cracks. As far as the terminology is concerned, in concrete structures we often talk of live cracks and dead cracks, and that is something which we measure or try to estimate using glass strips. The difference between these live cracks and dead cracks is that these dead cracks do not grow, whereas live cracks, they grow with time. What is being said is that if we have a beam and we have a crack something like this, we may have 2 cracks. If they are dead, this crack will not grow either in terms of width or in terms of depth from the surface over a period of time. If it was live, the crack might become wider or it might become deeper. So, it is important when it comes to crack measurements in concrete that we record this width and we record the depth to which the crack had been found at a particular inspection. So, sometimes we may say that okay, in June of 2020 the crack was here and it has grown to this place in June of 2024. The idea of glass strips is the following: across a cracked surface, that is, if we have a concrete somewhere here and this is the cracked surface, we put a glass strip, and if this crack was live, then this will tend to grow. That is, this surface and this surface will try to separate or become closer, or whichever way it goes, and in either case we would expect the glass strip to break. In other words, if in a concrete structure we fix a certain number of glass plates at different cracks, we can easily identify after a period of 3 months, 6 months, 1 year, how many of those cracks are live, that is they grow either on application of load or continued application of more cycles of load and so on, weather conditions and so on and so forth, or they are dead. That is, if a glass strip is fixed across this crack, it remains intact during different successive periods of inspection. It can be said that this crack is dead and is not growing. So, it is easier and perhaps better to have dead cracks than live cracks, because those live cracks indicate that the cracks continue to grow and could pose a danger as far as the future is concerned. Measuring these cracks involves the use of such magnifying glasses or a simple crack gauge. Now, this is a crack gauge which people working in this area often carry with them in almost their wallet. So, it is a very handy, easy to handle tool, as we shall see how to use this crack gauge in measuring the width of these cracks. Remember, however, that a crack in concrete may not be so well defined and continuous. So, let us see how we measure the crack width in a concrete structure as a demonstration. So, I already showed you this crack gauge, and what we have to do is to match the width on the surface with the crack width which is marked on this gauge. If we mark it carefully and try to see that which width corresponds to this width best. So, we will find that possibly something like 0.50 is better than 0.55 or 0.6 and so on. So, the width of this crack will be recorded as 0.5. We can always try to measure the crack width at different locations, and remember that cracks in concrete are not very well defined or continuous. So, it makes sense to have a system by which we will record the width at different locations. So, for example, 0.5 here, maybe it could be 0.45 here or 0.5 here once again. So, this is how we can record crack widths. Now, when it comes to crack lengths, on the same crack gauge we have a small scale which we could use to say that at a certain point in time this crack was 7.5 or 72 millimeters. So, this is the kind of record that needs to be maintained. Similarly, if we have another crack which measures, let us say 1.2 or 1.3, possibly 1.3 matches the best. So, if it measures 1.3 all over the place, so we can say that all over the place for this length which we will have to record. Let us see how much it is. So, let us say for about 53 millimeters, let us say the width is 1.3 mm. So, if you want to record the crack length along the crack, then of course, you have to do some other trick, measure it in different segments and try to see whatever best you can do. So, that is how we do measurement of cracks in the concrete surface, and obviously, this is an extremely tedious and a painstaking process. So, as far as the discussion so far is concerned, in this lecture we have talked about methods to yield information about the compressive strength of concrete and the cracking in concrete. I hope you appreciate the fact that the methods could be accurate. They can give us accurate information, but they are tedious to carry out, require close access to the structure and provide information only about a small area around the point of measurement or observation. And to cover for that, we need to take a large number of observations to have any firm understanding. Also, you should remember that as far as concrete structures are concerned, we could be talking about bridges, we could be talking about roads, we could be talking about buildings. Now, in each of these cases, the environment is different, the parameters are different, and there is a different degree of difficulty involved in carrying out non-destructive testing. While we will take the discussion forward in the next lecture, I will leave you with some food for thought. Study the standard test methods for using Schmidt hammer and the ultrasonic pulse velocity methods. What are the corrections that are required to be made before the raw data is ready for use? Find out the range of values as far as the UPV is concerned and how is it related to the strength or quality of concrete as far as the literature is concerned. When we talk of literature, we could be talking about papers, we could be talking about standards or guidelines which are published by different agencies. Please make a list of available Indian and international standards related to the tests that we have discussed. And here is a list of suggested reading and reference material that could be useful to you to understand the discussion that we have had today. And I would like to acknowledge all the help from my teachers, colleagues and students over the last several decades. Thank you.